Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to be using some data in order to calculate with the rate constant, the rate law, figure out what the rate law of a reaction is, and the order of the reaction. So let's get into this. So in this problem we have the following initial rate data, and it was collected at 25 degrees Celsius for the following reaction. We have 4A, where's 4A? 4A plus B plus C2 gives us A2B plus 2AC. So we have this generic equation here with A, B, and C as our reactants. And we're asked to identify the rate law for this reaction, the rate constant, and the order of the reaction using the data we have in this table. So let's get into this. Okay, so first thing you want to do to figure out the rate law is write out what the generic rate equation would be with your, what do you call it, variables, right? So here we have the rate is going to be equal to some rate constant K that we'll figure out later. And then we have these three reactants, A, B, and C. So we have reactant A, and that's going to be raised to some power. We'll call that X right now, multiplied by the concentration of B, raised to some power Y, and then that's going to be multiplied by some power, or so the multiplied by the concentration of C raised to the power of Z. So figuring out what the rate law is going to be for this reaction means that we're going to figure out what the X, Y, and Z are, the powers, and we'll have to figure out what K is as well, but that'll be a little bit later. Now, to figure out the powers, what we're going to do is we're going to look at the data, and we're going to take one reactant at a time. So we're going to isolate one of the reactants by picking two of the reaction experiments. So here we have 4 experiments. We're going to take 2 in which only one of the reactants differs in the concentration. The other 2 are held constant. So for example, let's take A. So we want to pick 2 experiments in which A changes, but B and C are the same. So we want to find 2 experiments where B and C do not change. So I have B is 3 for this one and 3 for this one. So B is the same between 1 and 3. What about C? I have 0.2 and 0.2. So C is also the same for experiments 1 and 3. But if we look at A changes from 0.2 to 0.3. So we can use that one. So the way we can do this is we're going to write the information into our equation here for both experiments 1 and 3. So let's go ahead and do that. So over here, I have, do I have space? Yeah, I'll write it here. So here for number 1, the initial rate is 6.8 times 10 to the negative 6. And then for 3, it's 1.0 times 10 to the negative 5. So this is larger. I'm going to write this one first. So for number 3, the rate is 1.0 times 10 to the negative 5. That's going to be equal to K times A. So for A, it's going to be 0.3. So we'll just put 0.3 here. And we'll have X for the exponent. And then we'll do the same thing for B and C. So B is 0.3. So we'll have 0.3 to the power of y. And then c is point, oops, wrong one, 0.2. So we have 0.2 raised to the power of z. So that's number 3. We're going to do the same thing for number 1. So for number 1, so the rate is 6.8 times 10 to the negative 6. And again, that's going to be equal to k times the initial concentration of A, which for number 1 is going to be 0.2 raised to the x power. And then for B and C, it's 0.3 and 0.2 again. So 0.3 to the power of y, and then 0.2 to the power of z. So now that we have the information for both of these plugged into our rate law, our generic rate law here, we're now going to divide both of these by each other. And when we divide, you'll notice that the k's are going to cancel out. Anything that's on the top and bottom are going to cancel out. So k's are going to cancel out. The 0.3 to the y's are going to cancel out. So this cancels out. And the 0.2 to the z's are going to cancel out as well. So everything cancels out except for the rates here and the concentrations with x. So if we rewrite that, we get 1.0 times 10 to the negative 5 over 6.8 times 10 to the negative 6 is equal to, and it's going to be 0.3 to the x over 0.2 to the x. So now we can solve for x. So we'll divide these two, and then we can divide these two as well. So if I continue over here, if I divide 1.0 times 10 to the negative 5 divided by 6.8 times 10 to the negative 6, I get 1.4705. So then 1.4705 is going to be equal to, and then since both of these are raised to the same x power, I can just combine both of these and have the fraction. So 0.3 divided by 0.2 to the power of x. Now to solve for x, you have to use your log, your log functions, right? So I take the log of both sides. So here, and then, but I can also divide this as well. So 0.3 divided by 0.2. So when I get that, I get 1.5. So if I rewrite this, I'm going to have 1.4705 is equal to 1.5 to the power of x. So now I can solve for x by taking the log of both sides. So here, I'll write it up here. So the log of 1.4705 is equal to the log of 1.5 to the power of x. Now, since I have log of something to the power of x, I can bring the exponent to the front. So the log of 1.4705 is equal to x times the log, the log of 1.5. And then I solve for x by dividing both sides by the log of 1.5. Divide this by the log of 1.5. So then x is going to be equal to 0.951. 0.951. And so x here is really close to 1. So we can round that to x is equal to 1. So the power of 1. And if we go back to the data, we can kind of see that here, that going from 1 to 3 here, experiment 1 to 3, we're increasing this by a factor of 1/2, right? So we're increasing this by from 0.2 to 3. So increasing this by a half, right? Because 50%, so 0.2, adding 0.1 is half of 0.2. So adding 0.1 to this, making it 0.3. So we're increasing by 50%. So you can look here that we're increasing approximately by the same amount, right? Keeping the other concentrations the same. So anytime you have a situation in which the factor by which you change your particular substance, the concentration of your substance, is the same as the factor by which the rate changes, that indicates that there is how do I say this, a factor of 1, meaning that the power of the substance you're looking at is 1, indicating that that is a first order rate, right? So it's going to be first order with respect to that particular substance. So in this case, we looked at A. So since the change in the concentration, the factor by which the concentration changes for A is the same factor by which the rate changes, that indicates first order, and therefore the exponent for that substance A is going to be a 1. And that's what we calculated here. X is equal to 1. So we know that that's a 1. So far, so good. But then we have to do the same thing for B and C. So we know that X is a 1 now, so we'll just replace that with a 1. And then we do the same thing for B and C. So let's go ahead and erase this. Okay, so now we pick 2 experiments in which B changes, but A and C are the same. So we look at A. Between 1 and 2, A is the same. And between 1 and 2, C is the same, but B changes. So now we're going to look at 1 and 2. So we look at the rate of 2, and that's going to be 2.7 times 10 to the 5th. So we'll write that. So experiment number 2, 2.7. So the rate is 2.7 times 10 to the negative 5. Okay, right here. And then that's going to be equal to K times the concentration of A, which in this case is 0.2. 0.2. And that's going to be at 1. And then for B, that's going to be at 0.6. So that's 0.6 to the power of y. And then C is 0.2. So 0.2 at the power of Z. And then we do the same thing for number 1. So we'll put number 1. So the rate is 6.8 times 10 to the negative 6. And again, that's equal to K times the concentration of A, which is 0.2 to the power of 1. And it's going to be 0.3 to the power of Y for B. And for C, it's going to be 0.2. 0.2 to the power of Z. Now that we have the information from those two experiments, we're going to then take the two expressions and divide them. Anything that is the same on the top and bottom are going to cancel out. So again, K's cancel out. The 0.2 to the 1 power, that cancels out. 0.2 to the Z power, those cancel out. So the only thing we're left with is this and this. So here we have 2.7 times 10 to the negative 5 over 6.8 times 10 to the negative 6 is equal to 0.6 y over 0.3 to the y. So now we do the same calculation and we solve for y. So we're going to take 2.7 times 10 to the negative 5 divided by 6.8 times 10 to the negative 6, and we get 3.9705. So we get, let's write this over here, 3.9705 is equal to, and then we'll divide those two. So 0.6 divided by 0.3 is 2. So this is going to be equal to 2 to the y power, because if I take 0.6 divided by 0.3, I get 2. So now this is equal to 2 to the y power. And so again, using logs, I can solve for y. So here, log of 3.9705 is going to be equal to log, oops, I forgot the log of 2y Now that I have y here, I can bring the exponent to the front. So the log of 3.9705 is equal to y times the log of 2. So now I'm going to divide both sides by the log of 2. And so now I can calculate y is equal to these two divided. And when I do that, I get 1.989. So 1.989. And that's really close to 2. So we can then round that to 2. So y is going to be 2. So we can take this and replace y with a 2. And now we can go to the table and I can show you how we could do that we could figure that out from the data here. So if we look at 1 and 2, you'll notice that the concentration here doubles, right? I go from 0.3 to 0.6. That's obviously double. So I'm doubling the concentration. But here, if you were to take these two and divide them, right? So going from here to here, if I take this, I get a factor that's pretty close to 4, right? So doubling the concentration of B leads to a quadrupling of the rate. So notice what the factor is here. So the factor, the change here is double, that's a factor of 2. And here it's a factor of 4. So the difference between the two factors is a factor of 2. So that means that this is a second order uh, reaction, or with respect to the concentration of B. So anytime that the factor by which your concentration changes differs by a factor of 2 with regard to the difference in the concentration change, then you know that that's a second order reaction. Remember, first order means that whatever the factor is that your concentration changes by is the same as the factor by which your rates change. Anytime that occurs, you know that the difference is a first order. But here, they're not the same. So this doubles by a factor of 2, but this changes by a factor of 4. So here it's 2, here it's 4. So the difference between the two factors is a factor of 2, right? So that means that indicates that you have a second order. The change here is second order with respect to B, which is what we calculated here. So if you know what you're looking for in the data, then you can translate that into that this is a second order, and therefore 2 is the number for the exponent. So first order means it's a 1 for the exponent, a second order means it's a 2, and that's what we calculated here. Okay, so now the last part is C. So now we need to find two experiments where A and B are the same, but C changes. So we look at A and B. We want A to be the same and B to be the same. So between 1 and 2, we already did 1 and 2, B changes. So we look at 2 and 4. 2 and 4, A is the same. What about B? 2 and 4, B is the same. What about C? C changes. So here we have a change in C. Here we have uh, A and B being the same. So we'll check 2 and 4. So we'll redo this. So 2 and 4, we're going to do the exact same thing with the data. So for number 4, we have 2.7 times 5 times 10 to the negative 5, and here we have 2.7 times 10 to the negative 5. So we'll do 4. So number 4, the rate is 2.7 times 10 to the negative 5 equal to K times A. So A is 0.2. 0.2 to the 1 power times B, which is 0.6. 0.6 to the second power, and then C is 0.6. Oops. Hold on a minute. Sorry about that. Okay, and then this is raised to the Z power. So next we do number 2. So for number 2, the rate is 2.7 times 10 to the 5 again. Negative 5, I mean, equal to K times 0.2 for A to the 1 power. For B, 0.6 again, 0.6 to the second power. And for C, it's 0.2 to the Z power. So we're going to divide these two. Once again, whatever's on the top and bottom will cancel out. So K cancels out. 0.2 to the 1 cancels out on the top and bottom. 0.6 to the second power cancels out. And then we have these two left. Notice here that 2.7 times 10 to the negative 5 is on the top and bottom. So that's going to cancel out to 1. So that means that we have 1 is equal to this here. So if I divide 0.6 by 0.2, I get a factor of 3. So 1 is going to be equal to 3 to the Z power. And once again, I can use logs to solve for Z. So log of 1 is equal to the log of 3 to the Z power. Again, the Z power can come to the front of the log. So the log of 1 is equal to Z times the log of 3. Divide both sides by the log of 3. And I get Z is equal to the log of 1 over the log of 3. Okay, now, if you know your logs, then you know that the log of 1 is 0, right? So if the log of 1 is 0, then that means we're taking 0 and dividing it by something else, right? Log of 3, but 0 divided by something is 0. So that means 0, the Z is 0. So here, the power is 0, and that means that the reaction is 0 order with respect to the concentration of C. And again, if we go to our table here, we could have gotten that just from the table, because you'll notice that even if between 2 and 4, we kept A the same. The concentration of A doesn't change. The concentration of B doesn't change. But the concentration of C changes by a factor of 3. But notice what happens to the rate of the reaction, or notice what doesn't happen. It doesn't change. The reaction rate stays the same, even though you change the concentration of C. That is a dead giveaway that your reaction rate is 0 order with respect to C, because the concentration, or I'm sorry, the rate does not change. So anytime your reaction rate doesn't change, even though you're changing the concentration of something, that is a dead giveaway that you've got a 0 order reaction with respect to that particular substance. So in this case, since the reaction rate didn't change, even though we changed the concentration of C, that tells us that it's 0 order with respect to C. So we have 0. So now we have our reaction rate law. Now, because this is 0 power, anything raised to the power of 0 is 1. So we can go ahead and get rid of that from our rate law. So this becomes a 1. So when we write out the rate law is finally going to be rate is equal to K, the rate law constant, multiplied by the concentration of A, multiplied by the concentration of B to the second power. So this, ladies and gentlemen, is the rate law for this reaction up here. Now, the second thing we need to find is the rate constant. To find the rate constant, now that we have the rate law, all we need to do is take any of these experimental data points and plug it into our rate law equation and solve for K. So let's go ahead and just take the information for experiment 1 and we'll plug that into our rate law. And so that's going to give us the rate, which is 6.8 times 10 to the negative 6. So 6, oops. So we have 6.8 times 10 to the negative 6. Is that right? Yep. Equal to K times the concentration of A, which is 0.2 to the 1 power. And then multiplied by B, 0.3 to the second power. And then because C is not here, we're not going to put C in. So now all I need to do is solve for K. So 0.3 squared, times 0.2, that's going to give me 0.018. So 6.8 times 10 to the negative 6 is equal to K times 0.018. Now I just divide both sides by 0.018. And I get K is equal to 3.78 times 10 to the negative 4. Now we need to figure out the units for K. So we got to go back here. Now the units for the initial rate is molarity per second, right? So this would be molarity per second. So if I redo this, we should actually redo it with the units just so you can see how we get the units for K. So for the rate, again, that was 6.8 times 10 to the negative 6, and that's molar per second is equal to K times A, and this is molarity, the concentration of molarity, so it's 0.2 molar. Oops. Times, and then B, it's 0.3 molar squared. So I'm not going to redo the calculation, but I'm going to show you, look, here we have molarity, and then here we have molarity squared. So molarity squared times molarity gives us molarity cubed. And remember, we're dividing both of these. So remember, we're dividing by 0.2 molar, 0.3 molar. Remember, these multiplied together was 0.018 molar squared, or molar cubed. So here, this is molarity cubed, so we're going to be dividing this by molarity cubed. But here we have molarity over seconds. So we have molarity cubed on the bottom, molarity on top. This is going to cancel out with one of these. So that's going to become a 2. So then our units is going to be molarity on the bottom. So this is going to be molarity on the bottom squared. So that's going to be m negative 2 if we bring it to the top. So that's going to be m negative 2 times S negative 1. Or, again, we could just put this like this. It could be 3.78 times 10 to the negative 4, and it could be 1 over meters squared times S, right? So either one works. It's just that 1 over meters squared is the same as, molarity squared is the same as molarity to the negative 2. So remember, 1 over x is the same as x to the negative 1, or 1 over x squared is equal to x to the negative 2. So that's what I'm doing here. So you can have 1 over molarity squared times S is second, right? Or you could bring these to the top, change the sign. So m squared on the bottom becomes m to the negative 2 on top. S on the bottom becomes s negative 1 on top. So this would be your the answer to the rate constant. So if we put that into our rate law now our rate law becomes rate is equal to 3.78 times 10 to the negative 4 molarity to the negative 2 times second to the negative 1, and then multiplied by A, concentration of A, times concentration of B squared. So there's the rate law with the rate constant together. Now, the last thing we need to identify is the order of the reaction. And the order of the reaction is the sum of the orders of the different of the reaction with respect to the different substances, right? So here we found that it was first order with respect to A, second order with respect to B, zero order with respect to C. To find the overall order of the reaction, you add up the orders of the different reactants. So 1 plus 2 is 3, plus 0 is 3. So the order of the reaction is 3. So that, ladies and gentlemen, is how you answer this sort of problem. I hope this was helpful. If you found this helpful or useful, or if you learned anything from this video, then please by all means like the video, share the video, hit that like button. Also, do me a solid, subscribe to my channel, help me out. If you do that, make sure you click the notification bell and click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.